Morning to everyone. So today we are going to see an important relation in thermodynamics, that is specific heat capacities and their difference and the ratio and their significance in understanding physical problems. So what is specific heat? So specific heat is a quantity of heat that is required to raise the temperature of a unit mass by 1 degree Celsius or 1 Kelvin. So it can be specific heat at constant pressure or specific heat at constant volume. Specific heat at constant pressure. So it is heat per unit mass per degree at constant pressure. So it is inferred that some energy does work as well as raising the temperature. That is the value of specific heat at constant pressure for air is approximately 1.005 kilojoules per kilogram Kelvin at 300 Kelvin. Specific heat at constant volume, heat per unit mass per degree at constant volume. So hence this is constant volume, there is no work being done in the system. So all the heat which is given is going for rising the internal energy of the system. So typical value of specific heat at constant volume for air is 0.718 kilojoules per kilogram Kelvin. So what is gas constant? So gas constant is difference between these two specific heats, that is difference between specific heat at constant pressure and specific heat at constant volume. So Cp minus Cv is equal to R. So this is difference between specific heats, that is gas constant, can also be derived as R is equal to R naught by M, where R is gas constant and R naught is universal gas constant, that is 8.314 kilojoules per kilogram Kelvin. Ratio of specific heats, gamma. That is the ratio of Cp and Cv. Cp divided by Cv. That is gamma. Cp is specific heat at constant pressure and Cv is specific heat at constant volume. So why understanding these parameters Cp, Cv, R and gamma are significant while studying thermodynamics? So energy exchange and process analysis. So when you add or remove heat from a substance, by knowing Cp or Cv, you can exactly calculate how much the temperature will change. So this underpins everything from sizing the heat exchangers to boilers, to predicting the temperature rise in rockets or chemical reactors. So Cp and Cv are important parameters. Thermodynamics cycle efficiency. In IC engines, work on air standard cycles such as Otto cycle, diesel cycle, Brayton cycle, and our refrigerator in our home work on refrigeration cycles. The work output or refrigerating effect directly depends upon Cp and Cv value of the substance. For instance, in Otto, diesel, and Brayton cycles, if air is the working fluid, it depends upon Cp, Cv values of air. If in refrigerator, the refrigerant, Cp and Cv value of refrigerant takes significance. The ratio Cp by Cv enters into expressions for ideal cycle efficiency, so that it will be essential for optimizing fuel economy and reducing emissions. Fluid flow and compressibility. Speed of sound in gas is given by A is equal to root of gamma into RT, where gamma is the ratio of specific heats of the working fluid. Sonic and supersonic flow behavior in nozzle, diffusers, wind tunnel testing, and it is critical in aerospace and high-speed aerodynamics. Heat capacity ratio and polytropic process. Many real processes aren't perfectly isobaric or isochoric, but follows a polytropic law, that is PV power n equal to constant, where n can be any value between 1 and gamma. So the choice of n and predictions of work and heat accurately hinges on Cp and Cv values. Molecular and statistical insights. So R value depends upon molecular weight, that is R naught divided by M, universal gas constant divided by molecular mass. Since Cp, Cv and R values can be worked around to get the molecular mass of the substances. Now we will derive Cp in terms of R and gamma. We know that Cp minus Cv is equal to R and Cp by Cv is equal to gamma. So in this equation, so we need only Cp in terms of R and gamma. So we have to get rid of this value Cv. So Cv can be rewritten as Cp by gamma. So we will substitute this value Cp by gamma in this equation. So we will substitute Cv equal to Cp by gamma in the equation. Cp minus Cv is equal to R. So Cp minus Cp by gamma is equal to R. So in these two equations, the Cp is a common term. So we will take Cp as common term, Cp into 1 minus 1 by gamma. In the next step, we will take gamma as LCM. Cp into gamma minus 1 by gamma is equal to R. In other words, Cp equal to R gamma divided by gamma minus 1. So this is Cp in terms of R and gamma. So next, we will derive Cv in terms of R and gamma. So Cp minus Cv is equal to R. So we need Cv in terms of R and gamma. So we have to get rid of this term Cp. So Cp by Cv is equal to gamma. Cp is equal to gamma Cv. So you will substitute Cp is equal to gamma Cv in the previous equation, that is Cp minus Cv is equal to R. So gamma Cv minus Cv is equal to R. So we will take Cv as common. Cv into gamma minus 1 is equal to R. And Cv is equal to R by gamma minus 1. So we have derived Cv in terms of R and gamma. Cv is equal to R by gamma minus 1. And Cp is equal to R gamma by gamma minus 1. So we can solve problems when you know only Cp and R or only Cv and R. Or we can derive other two terms if you know two terms out of these four. If you know Cp and Cv, you can derive R and gamma. If you know Cp and R, you can derive Cv and R gamma, and so on. Thank you.